Our Earth's moon is lopsided, and new research could finally explain why this is so. This is from Geoscience. It's on Science Alert by Michael Starr. The moon may be Earth's closest cosmic neighbor, and the only extraterrestrial body humans have ever set foot on up to now. There's a lot about it we don't understand. One of the biggest mysteries is why its two sides are so significantly different. Another mystery, of course, is why we only see one side. Now, researchers have proposed a possible new explanation. It's backed by experimental evidence. The moon's asymmetry, a recent paper lays out, could be down to an asymmetrical distribution of radioactive elements. The moon is tidally locked, which means one side, the near side, is always facing our Earth. When you look up at it, you can see it's covered in dark splotches, the lunar maria, wide plains of dark basalt from ancient volcanic activity inside the moon. Others say that they're impact craters. Anyway, going back to this, the far side facing away from our Earth is something that we never see, so that's a different story. The crust, for a start, is thicker there, with a different composition from the near side that faces us. The surface is also far paler, with few basalt splotches, and covered in craters. This is interpreted to mean that the basalt flows on the near side covered up a larger number of the moon's craters, but why the near side had more volcanic activity than the far side has been a pretty huge mystery that lunar scientists have been key to solve. There is something else peculiar about the near side of our moon, a geochemically weird region called the Porcellarum creep terrain, KREEP. It's unusually rich in specific elements, which gives its name K, the atomic symbol for potassium. REE is rare earth elements, and P is the atomic symbol for phosphorus. It also contains elements such as uranium and thorium, the radioactive decay of which generates heat, as we know. This Porcellarium creep terrain seems to be associated with basalt plains. It's been previously demonstrated that its heat-generated properties could have something to do with the near side's prominent volcanism. In fact, they said thermal modeling of the lunar interior suggests that the radioactive decay of potassium, thorium, and uranium could have provided a near-side heat source for billions of years. So, an international team of scientists set out to discover if this could be the case, and they conducted experimental analysis to gauge the effect of creep, KREEP, on the lunar rock. The mixed synthetic creep composition with lunar rock analogies at concentrations of 5, 10, 15, 25, and 50% creep. These were then kept at temperatures ranging between 1,175 and 1,300 degrees Celsius for between 4 and 8 days. The effect was dramatic from what the scientists found. The presence of synthetic creep in the mixture lowered the melting point of the analog, producing between 2 and 13 times more melt than in the control experiments without creep. And this is without the contribution of radioactive heat. To see what happens when this radioactive heat is added to the mix, the team conducted numerical modeling, and they found radioactive heating compounds that affect the effect of the creep, and together the two could have contributed to the volcanic activity in the moon's near side, resulting in the dark regions that we see today. As for where the creep came from, well, we still don't know the exact mechanism, but it's probably a consequence of how the moon formed. We think that happened about 4.5 billion years ago, when a body the size of Mars, Theia, slammed into Earth, sending debris flying into space, and that debris recombined into the moon, but not homogeneously. And gaining a greater understanding of how the Porcellarum creep terrain formed and affected the interior processes on the moon can help us better understand how it got there. Planetary scientist Matthew Lainville of Earth Life Science Institute in Japan said, because of the relative lack of erosion processes, the moon's surface records geological events from the solar system's early history. In particular, regions on the moon's near side have concentrations of radioactive elements like uranium and thorium unlike anywhere else on the moon. Understanding the origin of these local uranium and thorium enrichments can help explain the early stages of the moon's formation and, as a consequence, conditions on our early Earth. This research was published on Nature Geoscience, and it's on Science Alert by Michael Starr. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.